so topic 21 is going over the types of polynomial functions, and it's going to give us an introduction to rational functions. So the concepts we're going to go over is what is a polynomial function versus a rational function, how to find the vertical and horizontal asymptotes on a graph and in a function, how to find the domain and range of these functions, and then we're going to look at some applications of rational functions. So first, starting off with some definitions, a polynomial function is functions that only have positive integer exponents. So these are the functions that have x to the first power, x to the second power, x to the third power, so on and so forth. All positive integer exponents. A degree, the degree of a polynomial is the largest exponent in the equation. So, for example, in a quadratic equation, that degree would be what number? What's the largest type of exponent in a quadratic equation? 2, that's squared. So that degree for a quadratic equation is going to be square, or the 2. And then lastly, the fundamental theorem of algebra says the degree of a polynomial shows the maximum number of roots that the function can have. So for a quadratic, we know that the maximum number of roots, or x-intercepts, they can have is how many? For a quadratic? 2. The max is 2. They could have none, they could have 1, or they could have 2, but no more than 2. Okay. So we're going to look at some different polynomial functions that we've already went over. So in the first example, we have the function f of x is equal to c. Remember, this function was called a constant function. The reason it's called a constant function is because our f of x, or our y, was just equal to a number. So in this case, in this graph, we have y is equal to 1. Constant function. Remember, in a constant function, those are always going to look like a horizontal line. And since this does not have any x value, we say the degree of this function is 0, okay, because it does not have an x value. Okay. The next function, we have f of x is equal to ax plus c. This is what type of function? Remember the name? It forms a straight line, so this is a nobody a linear function. Remember, they form a straight line. Okay. I also know that this is a linear function because if I look at my equation, f of x is equal to ax plus c, what is the exponent attached to that x value? 1. So since that exponent is a 1, that means the degree of this function is 1. Remember, the degree is the highest exponent present. So for a linear equation, the degree is 1. What type of equation is this graph? What type of function? Quadratic. So this is a quadratic function. We know that from the U shape. Remember that U shape could be facing towards the top, or it could be facing towards the bottom. So looking at this quadratic function, what's the largest exponent we see?
Square.
That's square, so that means our degree is 2. Okay, so those are ones we've already went over. The next couple I'm just introducing. We're not going to go over them. Okay? So notice in this function, our largest exponent is that 3. So that means this has a degree 3, and this is called a cubic function. Cubic function. Those cubic functions usually look like how can I describe it? Never mind. I'm not even going to try to describe it. Lost my train of thought. Cubic function has degree 3. But if we look at the x-intercepts here, remember the fundamental theorem of algebra, that definition in the beginning, said if we have a degree 3, so a function that has the largest exponent of 3, that means we have 3 possible roots, which is true here. We have 1, 2, and 3. Okay. After the cubic function, any function with a degree higher than 3 no longer has a special name. They are just called polynomials of degree and whatever the exponent is. So this polynomial has the highest exponent of what? 4. So this is just called polynomial of degree 4. And that tells us that there are 4 possible what? Roots, which is true here. 2, 3, 4. Okay. And this can go infinitely higher. We could have a degree of 100. We could have a degree of 1,000. Typically, you don't see anything in these math courses and the courses coming after, anything higher than a 4. Okay. So that was just us naming these functions and determining the degree of each one. Any questions? Okay. Now we're going to look at the definition of a rational function. So a rational function are functions that can be written as a polynomial divided by a polynomial. The parent function would be f of x is equal to 1 over x, or we could write that as f of x is equal to x to the negative 1 power. Only important thing here is that it's a polynomial divided by a polynomial. Okay, and you'll see that later on when we look at those examples, the mathematical examples. Okay. So when you see the word parent function, that tells you that that is just the most basic the function can get. Okay. Other functions that are playing off of the parent function are called child functions. So parent function is the original / most basic. So for a rational function, they said that is y is equal to 1 over x. If I change the numerator or change the denominator in any way, that change is called a child function.
Can you change the what?
The numerator or the denominator of the parent function. Okay. And that could look something like, instead of y is equal to 1 over x, that could be y is equal to 3 over x. All I did was change the numerator to a 3. That is now a new function called a child function. which is part of the original parent function. The reason they divide it up like this is because all the traits of a parent function can be translated to the traits of a child function. So if we remember how to find the range, domain, and asymptotes of these parent functions, then we'll be able to find them for the child functions. Child function is not the proper name for it. That's just what I call it. So it's the parent function and the child function.
What's the proper name?
It's an excellent question. I don't remember the proper name. I've been calling it child function for so many years. It's just, I'm pretty sure it doesn't have like an official name. It's just a function that changes the parent function. So it's just like a translation of the parent function. But the child function makes more sense in my head, so. Okay, so looking at a rational function, y is equal 1 over x, this is what that function looks like. So it looks like we almost have two quadratics going in opposite directions. Okay. From these rational functions, we are able to find vertical and horizontal asymptotes. So an asymptote is one main characteristic of a rational function. A asymptote is a straight line where the function gets very close but never touches. So that's the important part here. The function gets close but never touches. Okay. So in these examples, looking at example 1, wants us to find the vertical and horizontal asymptotes on the graph. So remember, vertical, line going up and down. If we're looking at our graph, notice how these two rational functions are getting really close to each other, forming almost a vertical line in between, but they never touch that vertical line. So imagine this as our vertical line. See how this first function here is approaching that vertical line, but technically never touching it. And this one here is also approaching this vertical line, never touching it. Notice these graphs never go past the vertical line. They never go past it. That vertical line that separates those functions is called the vertical asymptote. This is the vertical asymptote. And remember, with a vertical line, we say that equation starts with what variable, y or x? It's x. X, because look how this vertical line crosses the x-axis. Where does it cross that x-axis? About 3. So that means the vertical asymptote is x equals 3. Okay. So using that same idea, now let's look at the horizontal asymptote. So if you were to take a guess, where do you think that horizontal line would lay?
3.
Good, yeah. Around 3 on what? What would our equation be? Y equals 3 because we're doing a horizontal line. Okay. Again, notice how our graph never passes over those asymptotes. So we said this one was y equals to 3, and this is our horizontal. Okay. So you're just looking at the spaces between each of the graphs. Okay. So looking at number 2, what would be our vertical asymptote? 2, good. What's the equation? Because we can't just say 2. X equals 2. And notice it's 2 because this graph is going by 2's. Right here. 2, 4, 6, 8, 10. Okay, so right here. So again, we say that this is x equals 2. Where would our horizontal one be? What equation? Good. Y equals -2. So when you're given a problem with a graph, this is all I'm looking for. For you to draw those lines, those asymptotes, and to give me the equations, not just the numbers, the equations. Okay. Okay, so this rational equation looks a little different, but it's the same type of concept. So looking at this, would we be able to find both asymptotes?
Yes. Wouldn't it have 2 x points?
Correct. It would have 2 of those yes, x points. What are those called? Which asymptote?
Vertical asymptotes.
Good. It would have 2 vertical asymptotes because we could draw something on this side and we could draw something on this side. How many vertical?
2.
Or sorry, horizontal? 1. Yep, it would just go around here. So knowing that, even though it looks a little different, we can have more than one vertical and more than one horizontal asymptote. Okay. So looking at the vertical asymptote, what's the one that's going to appear on the negative side? -3, correct, right here. And remember, I need that as a function, an equation. X equals -3. Where would the positive one be? Good. X equals +3. And where would the horizontal one be?
1.
And what's the equation? Y equals 1. Oh no. There. Okay. Go ahead and take a minute and try this one on your own. Finding the vertical and horizontal asymptote, and remember there's always a possibility that there's more than one. Okay, so what did you guys get for the vertical asymptote? Y equals 4. Good. Oops. So y equals 4. What about the vertical?
-1. Or -2. That is
Oh, wait.
x. Yeah.
You're right. You're right. Oops. And it wasn't +4. It was -4. For our -4? Yes, but for the purpose of this graph, we're going to go ahead and say -4 because I wouldn't want you guys to do like, okay, -3.98 something, you know? So as long as it's close, it's going to be accepted. And that's for the graph. When we get to the equations, that's a different story because you're going to be doing an exact math. Okay? And then what did you guys say for horizontal? 2. So y equals 2 right here. Okay. What do we notice about number 5? Good. The horizontal is going to be hard to get because are we able to draw a perfectly straight horizontal line anywhere on this graph?
No.
No, so that tells us that if we can't draw that horizontal line, then what does it tell us about that asymptote? It doesn't exist. So the horizontal asymptote does not exist. Remember, D and E does not exist. Okay, because we're not able to draw that straight line. This tells us that it does have a different type of asymptote that we don't cover in this course, but that asymptote would look something like this. It would look like a linear line. But again, that is not something that is taught in this course. Okay. What about the vertical asymptote? Do we have one? What would that be? Good, -2. What's that equation? X equals -2. Okay, so that tells us that there's also a possibility that our equations could not have a horizontal and could not have a vertical asymptote. Okay, last graph here, number 6. What would be the vertical asymptote? X equals 4. Yes, x equals 4. What about the horizontal? Y equals, yeah, 1, because it looks like it's just going up by 1s here. So y equals 1. Okay. So you definitely will have one question like this on the final.
Just one?
Just one.
Oh, just one?
Well, I'm trying not to make the final more than 20 questions.
There's 20 of these. Yeah.
Yeah. Okay, so looking at the next part, which means we'll have one of these, is how to find vertical asymptotes numerically. So we're given a function this time and not a graph. We're going to have to find this by doing some math here. Okay. The only one we are learning how to find in this course is just the vertical asymptote. Okay, just the vertical one. Okay, so if you are given an equation like this, I will only ask you to find the vertical asymptote. Okay. In order to find the vertical asymptotes, all we do is we set the denominator equal to 0. So in this example, our denominator is that x minus 6. So we do x minus 6 equals 0, which gives us what for our x value? 6. So that means x equals 6 is our vertical asymptote. So whatever the denominator is, we set that equal to 0 and solve.
That's it?
That's it. However, they're not always this easy. If we look at number 8, what do we notice about our denominator? It's a quadratic function. So if we set a quadratic function equal to 0, that means we have to use what to solve for x? Good, we could use the quadratic formula, that's one way. Or we could do what? Good, we could factor. So do the AC method and then do factor by grouping. So let's go ahead and just factor. Remember, in these type of problems, factoring may not always work, but the quadratic function will. Okay, so if you want to use the quadratic function for everything, you're more than welcome to. I always like to try to factor first because it's shorter. So trying out the AC method first, so we have A times C, which is negative 16, and B, which is negative 6. So what would be my two numbers that multiply to negative 16 but add to negative 6? Good, negative 8 and positive 2. So then we would expand this, and this would become x squared minus 8x plus 2x minus 16 equals 0. After the AC method, we always do factor by grouping. And I know that because there's 4 terms. So looking at my first parenthesis, what's the GCF I can take out? X, and I'm left with x minus 8. What about the next one? 2, and I'm left with x minus 8. Which is good because I want my parentheses to match. So that means I have the factors x minus 8 and x plus 2 is equal to 0. What property do I use now to solve for x? The what? Sorry? No. It's called the zero product property. And what does that zero product property tell us to do? Yes, set everything equal to 0. So that means I have my two answers of what? X equals 8, because I would add 8 to the other side. And x equals negative 2, because I would subtract the 2 to the other side. So this tells us I have how many...
2 degrees is squared.
Good, yes. 2 degrees means I have 2 possible answers. And that also tells us that I have 2 what? Asymptotes. Good.
So if we wanted to do the quadratic formula, what was that again? Is it that negative b?
Yes, it's the x equals negative b plus or minus the square root of b squared minus 4ac all over 2a.
And that will find the same answers?
Exact same answers, yes. How do we know that we have 2 asymptotes? Because we got 2 answers.
So if there's one answer.
Then there's 1, yes. And that is just because, remember, a rational function, like the ones that were graphed, means a polynomial divided by a polynomial. And that's what we have here. Yes?
How do you know the factoring method won't work? What will you get from your factoring?
Oh, okay, that's a good question. So if, let's say I went through this whole process and I got here, right, to the AC method, I would not be able to find 2 numbers that will work perfectly. So here I was able to find the 2 numbers, so that tells me that the factoring will work. If I couldn't find these, then I would go straight to the quadratic formula. Okay? Or even if these were possible, but you just can't think of what the choices are, you could go straight to the quadratic formula. Okay. So for number 9, in order to find the vertical asymptote, what are we going to set equal to 0? Good, x squared minus 4 equals 0. This is what type of equation? No, because what value is it missing?
Your c. No, your b.
Good, it's missing the b value. And then notice that that c value is a negative number that is a perfect square root. So what are these equations called? Perfect squares. Remember we did a section on that in one of the notes. Perfect squares. And remember, in order to factor a perfect square, we write our two parentheses. And in each parenthesis set, we are going to have a plus and a minus. And then we take the square root of the first term and the last term. So the square root of x squared becomes what? The square root of this. Good, becomes x because they cancel. So that means each one has an x. And what's the square root of 4? 2. So that means each one has a 2. Okay? That's how you factor perfect squares. Remember, perfect squares is missing the b value, and the c value has to be negative and a perfect square. So for example, before I finish this problem out, what if we had x squared minus 36? What would be the factors for that?
6.
Good, 6. It would be x plus 6 and x minus 6. What if we had x squared plus 9? Can that be factored as a perfect square?
Yes. Oh, no, because it's a positive.
Because it's a positive 9. So if it cannot be factored as a perfect square, then you use the AC method or the quadratic formula. Okay, it's only the case if this value is negative and a perfect square. Okay. I think we only did a short topic on that, so I just wanted to...
It has to be negative?
Has to be negative, yep.
And now we do the 0.
Correct. The 0 property tells us we do x plus 2 equals 0, x minus 2 equals 0. So I have two asymptotes of x equals negative 2 and x equals positive 2. Okay.
The reason we did this is because the x is squared, because like otherwise I thought you would do it like the plus 4 and then the square root of it and it would just have 1.
Correct. So since this x squared was there, we know it has a degree of what? 2. So that means there's 2 possible answers. So we always have to check to see if we could get 2 possible answers. You could do it that way and add the 4 over and then take the square root of each side. But you would have to remember that since this is a perfect square, that we're going to have one positive answer and one negative answer. Because if you were to plug that in, these numbers back in, no matter if the number was negative or positive, when you square it, it turns positive. Okay. Number 10, what are we setting equal to 0?
8x minus x squared.
Good. 8x minus x squared equals 0. Okay. Is this in the correct format?
No.
No. Why is it not?
Your a values at the end.
Good. So because that x squared is at the end, we know it's in the wrong order because it always goes largest exponent to smallest exponent. So that means I can rewrite this as negative x squared plus 8x equals 0. I took this entire term and just moved it to the front. Okay. So in this case, we're missing what value? The c value. And since we're missing the c value, this tells us before we start to try to factor, we can see if we can take out a what? A GCF. Can we take out a GCF here? What would be the GCF? Negative x. Remember, we always want to take out a negative if we have that negative attached to the a value. So if I take out a negative x, I'm left with what? X minus 8. Okay. When I took out the GCF, is this factored now? Yes, it is factored. So using the zero product property, that tells us to do what?
Set everything to 0.
everything to 0. So that includes that negative x. So if I set that negative x equal to 0, and I divide both sides by that negative 1 to get rid of that negative, I'm left with x is equal to what? 0. So that's my first one. What's my second one? 8. X equals 8. Again, I had that x squared in my problem, which tells me it's degree 2, which means I have 2 possible answers.
Essentially, could I use the quadratic formula again?
Yes, you could use the quadratic formula. Every single time, the quadratic formula will work. You would just have to remember here, if you are plugging these in, that this is the A value, B value, and what would the C value be since it's missing? 0. Okay. Okay, let's look at number 11. Okay, number 11, what are we setting equal to 0? The denominator. For this problem, I'm going to go ahead and use the quadratic formula to show you that either way works, but this is factorable. So if I'm using the quadratic formula, I'm labeling my A, B, and C value and writing out my formula. All I'm going to do here is start plugging everything into my formula. So I have x is equal to negative b. However, my b value is already negative, so I'm going to write a positive b, so I'm going to write a 2. Plus or minus the square root of b squared, so negative 2 squared, minus 4 times a, which is 1, times c, which is negative 8, all divided by 2 times a, which is 2 times 1, which is 2. So I'm just leaving the 2 as is. From here, you always simplify the discriminant first. Remember, the discriminant is what is inside the square root. So negative 2 squared is 4, and negative 4 times 1 times negative 8 is a positive 32. If we were to add 4 plus 32, we get 36. And is that a perfect square?
Yes.
Yes, that means we have x is equal to 2 plus or minus the square root of 36 over 2. We know that's a perfect square, so this is 2 plus or minus 6 divided by 2, which gives us 2 equations, one with that plus and one with that minus. So this gives us 2 plus 6 over 2 and 2 minus 6 over 2. The first one is 8 over 2, which is 4. And the next one is negative 4 over 2, which is negative 2. And if we would have factored this using the AC method and then factor by grouping, we would get the same exact answer, which with much less steps. But if you don't even want to bother with factoring, factoring's not your strong suit, use quadratic formula. It will work every single time. Anytime it does not work, then that means your answer is just going to be what? Does not exist. Yeah, does not exist or no solution. Okay. Go ahead and try number 12. This is another example of that perfect square. Remember here, because of that x squared, you're going to have two answers. Okay, what are the factors that you guys got for 12? Okay, just the factors, not the answers.
Oh, x plus 3 and x minus 3.
You had x plus 3, x minus 3, and that means the answers you got what? Good, x is equal to negative 3, and x is equal to positive 3. Okay, those are our two vertical asymptotes. Okay, any questions on how to find those?
How
Yes.
did you get the x plus 3 and the x minus 3?
Because I know that this is a perfect square because of this negative sign, and this 9 is a perfect square root. So because of that, I'm able to write my two factors, one with a plus, one with a minus, and then take the square root of that c value.
You get what she's finding.
Yeah, so these, for the perfect square, you have to meet this criteria up here. You have to have a missing b value, and your c value has to be negative and a perfect square. That's the only way you're able to get these factors. If it doesn't match that criteria, then you use the quadratic formula or you factor the AC method. Okay, so now that we learned how to find those vertical asymptotes mathematically and on a graph, we're going to use that in order to find the domain and range. So the domain uses those vertical asymptotes to find the restrictions on x. So we use the vertical asymptotes for the domain. Okay. For the range of rational equations, it is always all real numbers. So as long as you remember the range is all real numbers, when you're asked for the range, you could just write that fancy R, or negative infinity to positive infinity. Okay. So knowing that information, we're first going to find the domain and range of each graph, and then we're going to find it mathematically. So looking at number 13, okay, we're going to start with the range always because we know the range is what? All real numbers. Then we're going to look at the domain. The domain says we have to look at a vertical asymptote. So what's the vertical asymptote for this problem?
3.
Good, right here at 3. So I'm going to re-highlight that line that they have. That is at x equals 3. And remember, the definition of an asymptote means that the graph never does what? Never crosses, never touches. Meaning if we're writing the domain out, is x equal 3 going to be included? No, because it won't cross and it won't touch. That means it's not included. So when we write the domain, we're going to have to write it with those unions. Okay, and I believe we did this back in the beginning of the semester. So we know it's going to be negative infinity to 3. It's a parenthesis because it's not included. Union, parentheses 3 to positive infinity. So that means it's all numbers on this graph except when x equals 3.
What does union mean? I don't remember that.
Union, that U just means that we're combining both those parentheses. So when we have restrictions where we leave off numbers, we have to write it in multiple parentheses, but we write the union to say that this is all one answer. Okay. So just remember that the domain doesn't include the vertical asymptotes. Okay. And when it doesn't include something, we call that a restriction. So that means our domain is all real numbers with a x equals 3 restriction. And we write that with the union. Okay. So on number 14, starting with the range, we know range is always all real numbers. And then looking at the domain, we first need to find the what? Vertical asymptote. And what is this vertical asymptote here? X equals 4. So that means, are we including the 4 or not including the 4? Not including the 4. So when I write this, I always start off with negative infinity. And then I go to the number we are not including, which is 4. And I put a parentheses, because parentheses means we're not including it. Union, and I start off with that number we're not including again, so 4, all the way to positive infinity. So again, this is just a way to say that the domain is all real numbers except 4. Okay. Go ahead and take a moment and work on the domain of 15. Because we already know that the range is all real numbers. What number is our restriction? 1. So our domain, you should have negative infinity to 1, union 1 to infinity. Every number except 1. And then we're skipping 16 because I accidentally put the same graph. This is the same.
So it's a parentheses, not a bracket, because it's not included.
Correct.
Okay.
Correct. Okay. Now we're going to do some examples where we have our rational equations written mathematically. Okay. And they're asking us to find the domain and range. So remember, we say that range is always all real numbers, even when we see an equation and not a graph, all real numbers. And for the domain, we're going to have to first find the what? The vertical asymptotes. So remember, we said in order to find those, we set the denominator equal to 0. Since it's a quadratic equation, we can choose to factor or we can choose to use the quadratic formula. But before you do either method, is there a GCF that we can take out of the entire problem? Negative 2, because remember, we don't want our a value to be negative. So we take out a negative 2, and we're left with x squared plus x minus 6 equals 0. We took out that GCF. Okay? So that means we're only looking at this inside parentheses in order to factor. So if I write the AC method, I get A times C, which is -6. And our B value is 1, since there's not a number in front of X. So what would be two numbers that multiply to -6 but add to 1? Good, 3 and -2. So I have x squared plus 3x minus 2x minus 6 equals 0. After the AC method, I always do what? Factor by grouping. And what's the GCF I can take out of the first one? X, so I'm left with x plus 3. And I want my parentheses to match. So what would I take out of the second one? Good, a -2, so I'm left with x plus 3. Okay. That means I have x plus 3 and x minus 2 is equal to 0. Okay. So that means I have x is equal to -3 and x is equal to +2. So again, these are not my answers, these are just my vertical asymptotes. So instead of just having one asymptote, we have two. So that means instead of having one restriction, we have two restrictions. So our domain is going to look a little longer than just that two parentheses with one union. Because remember, the only numbers that we can't have is -3 and 2. We can have every other number. So you always start off with that -infinity. So -infinity, and then you grab your smaller number. Yes?
What about the -2 we took out at the start?
Since that -2 does not contain a variable, it's not going to do anything to our roots. Because yes, technically we would bring it down if we were factoring. But if we do -2 equals 0, that's a false statement. So it doesn't do anything to our problem. Okay. So going back up to the domain, we do -infinity and then our smallest number, which is
-3.
-3. Okay. Parentheses, union. Okay. Remember, we always start with that number that we just wrote. So I'm going to start with -3, and I'm going to go to my next number, which is 2. Then I'm going to write a union and start with my last number again, which is 2, and I'm going to go all the way to infinity. Oops. So if you have two answers, your domain is going to have 3 parentheses. If you have one answer, your domain will have 2 parentheses. Because this domain tells us that it is including every number besides -3 and 2. Okay, let's look at 18. Okay, we know right away the range is what? All real numbers. And in order to find the domain, we have to find what first? The vertical asymptote. So x squared minus 3x minus 4 equals 0. That x squared tells us it's a quadratic. So I'm going to try to factor. So I have A times C method, which gives me -4 and my B value -3. So what would be my two numbers that multiply to -4 but add to -3? -4 and 1, yes. Okay. So expanding this, I have x squared minus 4x plus x minus 4 equals 0. Which means I'm doing factor by grouping. What can I take out of the first parenthesis? X, so I'm left with x minus 4. And I want my second parenthesis to match, so what am I taking out? A 1. Because if I take out a 1, those parentheses does not change. So that means I have the factors x minus 4, x plus 1 equals 0. So that means my two vertical asymptotes are what? 4 and negative 1. Okay, so that means my domain is going to have how many parentheses? 3, because I have 2 answers. And my parentheses are going to start off looking like what? What comes first? Negative infinity, and then what? Negative 1, because it's my smallest number. Union, what's next? Negative 1 comma 4, my other number. And then union, what? 4 comma infinity. Any questions so far? Okay. And then I'm going to go ahead and skip 19 because it's very similar to 17. The only thing that's different is that negative. So, similar to 17. And then we're going to go to 20. So we know our range is always all real numbers. And in order to find our domain, we're going to set what equal to 0? The bottom, the denominator. Okay. When I set this equal to 0, this looks like what type of equation? Perfect square. Because of that negative, because it's missing the b value, and because 1 is a what? Perfect square. So that means I'm going to have x minus 1 and x plus 1 equals 0, because the square root of 1 is 1, which means I have x equals 1 and x equals negative 1. So those are my two restrictions, my two asymptotes. So how am I writing my domain? Good. Negative infinity to negative 1, my negative number. Union what? Negative 1 to 1, because I always start with that number that I ended with. Union, and what's last? 1 to infinity. Okay, so we learned how to find these asymptotes, both on a graph and mathematically, and then how to find the domain and range. Okay. Last concept here, we're going to look at some applications. And in application problems, a lot of real-world problems do use rational functions. So that polynomial divided by another polynomial. So looking at 21, it says heavy metal contaminants in a cement quarry may be removed from the soil by planting sunflowers. Use the following model to estimate the number of sunflowers S, which is in thousands, needed to remove P% of the contamination. So it says note that P is a percent. So 25% means that P is equal to 25. Okay. So we are given this equation. S of P is equal to 90 divided by 100 minus P. It says, how many sunflowers would it take to remove 50% of the contamination? That 50% is what variable?
What's your P?
Is your P, and what are we plugging in for P? 50. So I'm going to take my equation, S of P, so S of 50 is equal to 90 divided by 100 minus 50. So anywhere I saw a P, I plugged in a 50. Simplifying this, I have 90 divided by 50, which is the same as saying 9 divided by 5, which is 1.8. However, it said that our S value is in what? Thousands. So what do I need to do to that 1.8? Multiply it by 1,000, or, yes, add 3 zeros to the end. So that means we have how many sunflowers?
18,000.
1,800 sunflowers. Just because of that decimal there. Okay, so we're using our knowledge here and just plugging in whatever it tells us to plug in. The next one says, how many sunflowers would it take to remove 99% of the contamination? Where are we plugging in that 99? P. So I have S of 99 is equal to 90 divided by 100 minus 99. So that gives me 90 over 1, which is 90. And I'm going to multiply that by 1,000. So I get how many sunflowers? 90,000 sunflowers. So to get rid of 99% of the contamination, they would have to plant 90,000 sunflowers. Next question says, what percent removal cannot be achieved? Why not? Good. Why can't 100% be achieved?
Because
Negative sunflower.
no, because you'd have, it would equal to 1. And 1 times 1,000 is just 1,000, and that's way less than 90,000.
No. Any other guesses?
Oh, it equals to 90,000 again, right?
No.
Because
Yes.
100 minus 100 is 0, and you can't divide by 0.
Correct. So if we did S of 100, that's equal to 90 over 100 minus 100, which is 90 over 0, which is undefined. Okay, so we can't reach 100% because the denominator would equal 0. Okay, that doesn't mean we can't achieve 99.99999%, right? We can just never achieve the perfect 100 because we would get an undefined answer. Okay. Any questions on 21? Yes.
Is it gonna be like more or less like that on the test, or are you gonna give us like?
It will be like this, yeah. Yeah.
So in the real world, is this legitimate? You can't pull 100% of the heavy metals if given this statistic?
Correct.
That's crazy.
That's why on a lot of things they say like on disinfectant, you know, it says 9.99998% effective because they can never guarantee 100%, because if they're using a model like this, it would get close to 100%, but it would never be exactly 100%. So they can't guarantee that when they're putting that on the product.
Or something crazy. It's Lysol and hand sanitizer.
Okay. 22 says it costs money to keep a lake clean. Say there are 2 tons of pollution in the lake and the cost C in hundreds of dollars of removing X tons of pollution is the following. So X tons of pollution, C is in hundredths of dollars. So it says how much would it cost to remove half a ton of pollution? Okay, half a ton. So half a ton we can write as what number? Good, 0.5. And pollution is what variable? X. So that means wherever we see an X, we are plugging in 0.5. So C of 0.5 is equal to 70 times 0.5 divided by 2 minus 0.5. Okay. Simplifying this, we get 35 divided by 1.5, which is approximately 23.33. Okay. But remember, our cost is in what?
Hundreds.
Hundreds. So what are we multiplying that number by? 100. So that means the total cost is going to equal $2,333. For these applications on the rational equations, all the applications are going to be simple like this. It's just plugging in a number. Okay. Next part says, explain what happens if they attempt to remove all 2 tons of pollution. So this is similar to that last problem.
They can't.
Good, they won't be able to. So let's say we plug in the 2. We're humoring them plugging in the 2. When we plug in that 2, what happens to the denominator? It becomes 0, which means it's undefined. So that means if they attempt to remove all 2 tons, they can get really close to that, but they're not able to remove all of it. So they won't be able to remove 100% of it. Any questions on 22? We have one more. On this application, we're given a graph. It says a typical round of golf is 18 holes, where your cumulative score for the round is the sum of all the shots you took on each hole. For example, if you took 4 shots on each hole, your score is 4 times 18, which is 72. So that's just explaining what this graph is representing. It says, describe the relationship between the rounds of play and the score on 18 holes. Okay, so here's the score on 18 holes, right? This is the number of rounds. So we could say this is 1, 2, 3, 4, 5, right? What is that relationship between the rounds? So what is the graph doing? As you play more rounds of golf, what is happening?
You're doing more shots. More shots, more rounds. No, more rounds, more shots.
Because it's going down, so it's saying that the least rounds you play, the higher your score. Because as we're going down here, this is going out this way. So it says as you play more rounds, your score, more rounds, the lower your score gets. I think that's opposite. So we're going to say the more rounds means the higher the score. Then it says, looking at the graph, what scores are impossible and why? So remember, we're looking at that restriction. What's the restriction on this graph, the vertical asymptote? Good, 18. So it's saying that a score of 18 is impossible. Why? So 18 or less is impossible.
So you have to take more than one shot on each hole.
Good, because they're assuming you're taking more than one shot on each hole. So it says a score of 18 or less is impossible because you can't take less than one shot on each hole. Okay, so score of 18 or less is impossible because you have to take at least one shot. Okay. And then that's it.